Let's take a look at another functional equation, which is the problem 2 of the International Mathematical Olympiad 1992. It says, find all functions f from real number to real number such that f evaluated at x squared plus f of y equals y plus f of x quantity squared for all x and y are real numbers. And let's call the original function equation p of x comma y. Okay, so let's start by plugging in initial value to the original function equation to see whether we can simplify it. So let's try p of 0 comma y. Okay, so on the left side we have f of y equals y plus f of 0 quantity square. Okay, so and let's try to manipulate the original function equation to see whether we can do some simplification furthermore. Okay, so let's do some observation. We can see that there are similar structures on both sides. Namely, we have the quadratic term x squared on the left side and f of x quantity square on the left side. We also have a first order term on both sides, f of y on the left side, y on the right side. And we will take f on the left side, we don't take f on the right side. So let's see whether we can try to take f on both sides, and then we try to use the left side to the right side. Okay, and then we can do some simplification. Let's write it out. So we have f of x squared plus f of y equals y plus f of x quantity square. Okay, so let's try to take f on both sides. So it looks like this: f of the both sides equals to each other. And then let's see whether we can just put in the left side of the functional equation and apply to the right side to this equation. Okay, so first of all, we can see we can just change x to f of x, which means p of f of x comma something. But actually we cannot change f of y to y because so far the inverse function is not defined yet, so we cannot just change f of y to be f of y inverse, something like that. So but actually we can manipulate the original function equation, which means we can just try to pick it like p of x comma f of y like this, which means that we just replace y by f of y like this. Okay, so here we just only need to have p of f of x comma y, and then this should be the left side of the original function equation, and then it should be equal to y plus f of x quantity square. Okay, then here we can just, so let's call this one equation 1. Here we can apply equation 1 here, and we replace y by x. Okay, so we have y plus parenthesis, open parenthesis, x plus f of 0 quantity square, and then the whole term square. So it will become y plus x squared plus 2x f of 0 quantity square plus f of 0 to the 4th power. Okay, so we have extract the right side of the function equation. So let's see whether we can also simplify the left side. Here we have f of y, so we can apply the equation 1 directly. Okay, so we have f of x squared plus y plus f of 0 quantity square, like this. Okay, so here we have f of f again. So we can also apply equation 1 with y replaced by x squared plus y plus f of 0 quantity square. So it becomes x squared plus y plus f of 0 quantity square plus another f of 0 quantity square. So we altogether have 2 f of 0 quantity square. And then here, this side should be equals to that side. And here we can do some cancellation. We can cancel x squared on both sides. We can also cancel y on both sides. And then we can try to find out what should be f of 0. So let's try to move this over and swap left and right side. So we have f of 0 to the 4th power plus 2x times f of 0 quantity square minus 2 f of 0 quantity square equals 0. And then we can factor out f of 0 square. And then we have a f of 0 quantity square plus 2x minus 2 equals 0. Okay, so here, as much as the two expression multiply to be 0, which means that f of 0 quantity square to be 0, which means f of 0 should be 0. Or f of 0 quantity square plus 2x minus 2 to be 0 for all x in real number. But this is not possible because x are arbitrary value, so it can't be always 0. So we don't have solution for this one, which means that the only solution is f of 0 to be 0. And we can plug in this one into equation 1 and have some simplification. So for equation 1 with f of 0 to be 0, we have f of y equals y for all y, a real number. And let's call it equation 1 prime. Okay. And for the original function equation, let's try to do some simplification so that it somehow look like the Euler's equation, although it does not actually the same. So original function equation is like f of x squared plus f of y equals y plus f of x quantity square. Okay, so here let's try to make it like p of x comma f of y. Okay, so this one become f of y, and here it is f of y, and then we can apply 1 prime. So with 1 prime, so we have a f of x squared plus y equals f of y plus f of x quantity square. And let's call it equation 2. So here we need to prove some property for the function f. So let's start by proving it. To prove f is injective. F is injective. Okay, f is injective is easy to prove, because suppose f of m equals f of n. Of course, m and n are real numbers. And then let's take f on both sides so that they should still equal to each other. So we have f of m equals f of n. But with equation 1 prime, and of course we can just substitute y to be m and n respectively. So we have m equals n. So this is proof. Okay, so the first property is proof, f is injective. So let's move on to the second property. Okay, to prove f is strictly increasing. Okay, so first of all, as much as f is injective, and f of 0 is 0. So for all r is not equal to 0, f of r should not be equal to f of 0 equals 0. Okay, which means that is f of r is not equal to 0. Okay, so next, suppose z is larger than y, then we can write that z should be y plus a positive number. We can just write it as r squared, and of course z is strictly larger than y, which means that r is not equal to 0. It can be positive or negative number, as much as r squared would be a positive number. Okay, so here, so in equation 2, okay, we just change x to be r. So here we will have f of y plus r squared equals f of y plus f of r quantity squared. And then here, y plus r squared will be z, so f of z should be equal to the left side. And then this one, as much as f of r is not equal to 0, so f of r quantity squared should be a positive number, which means that f of r quantity squared should be larger than 0, which means that this side should be larger than f of y. So we have f of z is strictly larger than f of y. So we prove this property also. Okay, so as much as we have proved these two properties, then we can try to prove f of x is x for all x in real number. Okay, so let's prove it by way of contradiction. So suppose there exists x sub 0 in real number such that f of x sub 0 is larger than x sub 0. Okay, because we want to prove f of x to be x for all x. So let's try to assume if there is a single value x sub 0 such that f of x0 is larger than x0. Okay, and as much as f is strictly increasing. So let's take f on both sides, so the inequality wouldn't change the direction. So we should have f of x sub 0 is larger than f of x sub 0. And using equation 1 prime, we have x sub 0 is larger than f of x sub 0. Okay, so these two equations are contradict with each other. So there doesn't exist x sub 0 such that f of x sub 0 is larger than x sub 0. And similarly, we can also suppose that there exists x sub 0 in real numbers such that f of x sub 0 is smaller than x sub 0. Okay, and as much as f is strictly increasing, so when we apply f on both sides, the inequality doesn't change the direction. So we also have f of x sub 0 is smaller than f of x sub 0. And then we will have x sub 0 is smaller than f of x sub 0, and then it will contradict with the assumption. So there doesn't exist any value such that f of this value doesn't equal to itself, which means that by way of contradiction, we have proved that f of x should be x for all x in real number. Okay, so let's check whether this solution satisfies the original function equation. So on the left side, it is f evaluated at x squared plus f of y equals f of x squared plus y equals y plus x squared equals y plus f of x quantity square. So check. So in other words, f of x equal x is the only solution for the functional equation, and this is the end of this video.